Alright, today I want to talk about factoring some special polynomials, and all of the polynomials in these two categories have to do with the concept of squares. And the first one is about perfect squares, and just in terms of numbers, you know that a perfect square, such as 9, is a number that can be written as 3 squared. And visually that can be thought of as a 3 by 3 square that has 9 little squares in it, an area of 9. Alright, now we can do a similar thing with a polynomial, and today we're going to talk about taking a binomial and squaring it. So what I'd like you to do is just take a few minutes and turn off the video and multiply the three expressions that I have below out and see what you get. And specifically, I'd like you to look for patterns in terms of the way the answer works out. Alright, now that you've multiplied the three polynomials out, let's just take a look at some shortcut patterns that may exist, because you can certainly multiply these out doing what we've done here. But what I'd like to be able to do is to go from here directly to here. Now before I do that, let's just remember visually what this expression represents. It represents a square with side lengths that are identical, x plus 3 by x plus 3. Okay, so if I let my x represent that amount on each side and my 3 units there, and I break my big square up into its component parts, I can see that the sum of those parts would be an x squared, which is here. I have 3 strips of x and another 3 strips of x here, so I have 2 sets of 3 strips. And then I have my 9 1 units at the end. So now let's look to see if we can get some shortcuts that'll take us from this binomial directly to this trinomial that's expanded out. The first term is x squared, and we got that by going x times x, which is identical to just squaring the first term. The last term in the expansion is the square of the last term in the binomial. And that relates to this section up here on the picture. The middle two terms are identical, and they come from the outside and the inside. They come from the fact that we have 3 strips here and 3 strips here. Now a shortcut to getting this would be to think of the fact that we have 2 sets of x times 3, which is 3x, and that's 6x. So what I'm saying is, to get that middle term, if we multiply these and double, we will get this. Multiply and double. Multiply these two terms in the binomial and double it to get the middle term in the expansion. Alright, let's just confirm that that shortcut works for these other two examples. So to get the first term, I would square the first term in the binomial. To get the last term in the expansion, I'd square the last term in the binomial. So negative 2 squared is plus 4. And to get the middle, we are going to have 2 sets of x times negative 2. So the product of those two would be negative 2x, and we'd have 2 sets of those, so we would have 4x. Okay, one last example. We have a binomial squared, as we call it. And so we square the first term to get 4x squared. We square the last term to get plus 9, which is the last term in the expansion. And we multiply the two terms, negative 6, double that to get negative 12x. And all of these answers that we're getting we call perfect trinomial squares. Because if we were to go in reverse, which is where we're headed with this, this trinomial factors perfectly into a binomial squared. It's a perfect square. So what do we notice about all of these answers? How are we going to be able to identify when something's a perfect square and when it's not? Alright, to answer that question, you'll notice that in all of the expansions in the questions above, the first and the last terms were always perfect squares. The middle term, remember, was twice the product of the two terms in the binomial. So we have to look for that pattern when we're trying to decide whether something is a perfect trinomial square or not. Alright, let's take a look at the examples here. So in number 1, I am trying to make this a perfect trinomial square by inserting the right number in the blank. So the first thing I need to look for is I have perfect squares at the front and the back. And so that means that in the binomial, that must be x, and this must be 3. Now what I need to check is that these two multiplied together, doubled, will give me this. And for that to happen, this would have to be a 6. Alright? Our second example, another perfect trinomial square. So again, these two numbers must be perfect squares. So the square root of x squared is x. Now we don't know what the last term is, so we're going to have to remember that whatever these two terms are, if we double them, we're going to get 10x. Well, if doubled it's already 10, half of that would be 5, so that would mean that this could be minus 5. X times negative 5 is negative 5, doubled is negative 10, and then if we square the last term we get plus 25. Okay, so hopefully you're catching on to the pattern now. And so we can now take this and apply it to the factoring of trinomials in general. Okay, but we have to look for the pattern we've just talked about. So here's a trinomial, and the question is, can I break it down into something squared? The answer to that is yes, if the first term's a perfect square, which it is, the last term's a perfect square, which it is, and the product of these two doubled, so 3x times 5 is 15, doubled is 30. And since it's negative 30, my negative will go there. Okay, just try the last one on your own. Stop the video for a second and try it. Alright, so the question is it a perfect square? Looks like it has the potential to be, because we have perfect squares at the front and the back. Square root of 25x squared is 5x. Square root of 49 is 7. If I multiply these two, I get 35, and if I double it, I get 70. If when I multiplied and doubled, I didn't get 70, that would mean that this was not a perfect square. It wasn't possible to write it as something squared, and I'd have to try some other methods. But in this case it is, and I'm good. The second type of factoring related to squares is called difference of squares. So again, I'd like you just to take a moment to shut off the video, multiply these three binomials out, and see what you get and see if you notice any patterns. Okay, for the first expression I've just drawn a picture to visualize what's going on. We have x plus 3 along here. Both x and 3 are positive. Along the side we have positive x and negative 3, so I've got the negatives in red. And then when I go positive times positive, I'm going to get x squared here. These rectangles down here will be negatives because I'll be positive times the red, which is negative. So I'm going to shade these red to be negative strips. Up here, this will be positive 3 times positive x, so these will all be positive. And down below we'll have positive 3 times negative, so these will be negative here. Okay, and so what I get from the picture is I get x squared. 3 negative strips and 3 positive strips cancel out to give me no strips at all. And then we've got the 9 negative strips. And so I get x squared minus 9. So what you've probably noticed in doing all three of these examples is that when you expand it out, the two inner terms cancel out, and your answer is a binomial. So the multiplication of these two binomials usually produces a trinomial. In this case, it's producing a binomial. Okay, and the reason it's doing that, I'm sure you figured out, is the fact that the two terms are identical except for the sign in the middle. First, outside, inside, last, the outer and the inner cancel out, and you're left with two terms with a subtraction sign in between. Alright? So if you notice the pattern where you have two identical binomials except for the middle sign is opposite, you can simply square the first two terms, 16x squared. You know, having done this, that the outside and the inside will cancel out, and then multiplying the last terms you get minus 9. Okay, and this pattern we call a difference because of the fact that the sign in the middle of the expansion is a subtraction sign. A difference of two perfect squares. You'll notice in all of these examples the two terms are perfect squares with a subtraction sign in the middle. So if I want to go in reverse, if I look for this pattern where I have a subtraction sign and two perfect squares, I can go in reverse with this pattern. X squared minus 100. It's the subtraction of two perfect squares. So by what I saw above, I know that the first term would be the square root of x squared. The last term will be the square root of 100. One gets a plus, one gets a minus. Okay? This pattern only holds if there's a minus in the middle. If I have x squared plus 100, that is not factorable. Go ahead and try all you want to factor it in a whole bunch of different ways. It will not work. So this is prime. It cannot be broken down. Finally, a more complicated situation. Again, we have a subtraction of two perfect squares. So the pattern will be something plus, something minus. The square root of this is 9x. The square root of that is 8y. And so my polynomial is factored. And it turns out I do have one more example. Now, down below, I will notice that I don't have a difference of squares, but what I do have to start with is a common factor. And when I'm factoring, I always want to look for this first. Is there something that goes into both terms? Well, in this case, 2 and x comes out, and that leaves me with x squared minus 4. If I distribute that back, I get this. Now, this second factor is what we just talked about above, a difference of squares. So it can be broken down further into x minus 2, x plus 2. And now my polynomial is fully factored.